In my previous video, I discussed Dijkstra's algorithm for finding the shortest path from one vertex in a graph to all other vertices. Now here I want to talk about another algorithm which accomplishes the same thing but in different situations. So if you have not watched the video about Dijkstra's algorithm, click on the eye icon on the top right corner and go watch it right now. And after you have watched Dijkstra's algorithm, watch this video to understand what happens if I change some fundamental properties of the graph. And if you like this video, do not forget to hit the like button. Also comment down below of your feedbacks, suggestions, anything. So let's get started. This time our graph has changed quite a bit. First of all, it is directed, which means that every edge or path has a certain direction, as indicated by the arrows. For example, you can go from 0 to 1 but cannot go from 1 to 0. Now this is strictly not a problem for Dijkstra's algorithm. The algorithm would work for directed graphs as well. However, this time some of the edges have negative weights. Now presence of negative weights will cause Dijkstra's algorithm to fail. This time we use an algorithm known as Bellman fold. Now this can work with negative weights as well as it can detect negative cycles. Now before we proceed, what are negative cycles? So negative cycle is a loop whose sum of weights is a negative number. As an example, consider this graph. It is a loop from 0 to 1 to 2 and then back to 0. Now the sum of weights is minus 2. This is a negative cycle. Now how does presence of a negative cycle cause problems? So let's try to find the shortest path from 0 to 2. Of course the shortest, well in this case actually the only path, is from 0 to 1 and 1 to 2 at a total cost of 1 plus minus 2, which is minus 1. Now if you go to 0 right now, your total cost becomes minus 2. Now if you follow the loop once more and come to 2, the total cost will be minus 3. If you do this once more, the cost will be minus 5. So the more you loop, the lesser the cost. In other words, there is no shortest path from 0 to 2 because you can just keep looping and the cost will keep decreasing. Now this is a problem. So Bellman fold algorithm can actually detect the presence of a negative cycle. In case of a negative cycle, we just say that there is no shortest path, or we can say that there is a negative cycle and stop the algorithm. So the algorithm starts quite similar to Dijkstra's. We start by creating a list of distances of each vertex from the source vertex, which in this case is 0. Then we set the distance of vertex 0 as 0 and the rest as infinity. Now in Dijkstra's algorithm, we visited each vertex once, but the case is different here. We have to loop for at most the number of vertices minus 1 times. So here we have 6 vertices, so we have to loop at most 5 times. Now we might not need all 5 iterations, but certainly no more than 5. And in each iteration, we will have to look at each edge. Now looping over edges can be quite unorganized, so we can instead loop over all vertices and look at all the outgoing edges. This will make sure we look at all edges. So let's start the first iteration. So we start from vertex 0 and look at the 2 outgoing edges. Now we have got a new distance of vertex 1 and vertex 5, which are less than the existing infinities, so we update them in the table. Kind of similar to Dijkstra's. Now let's move to vertex 1 and see its outgoing edge. So we got a new distance for vertex 2, which is 8 for going from 0 to 1, plus 1 for going from 1 to 2. So a total of 9. And 9 is less than infinity, so we update. Then we move to vertex 2 and look at its outgoing edges. Now for vertex 3, we have a new distance of 9, which is the distance for 2 and then minus 1. So we get 8. And this is a better distance, so we update it. Now for vertex 5, we have a new distance of 9 for vertex 2 and then plus of minus 3, which gives us 6, which is less than what is existing there, 10. So we put 6 there. Now on to vertex 3. This gives a new distance for vertex 4. So distance of 3 is 8 and minus 2, we get distance of 4 as 6. Now we go to vertex 4. We again get a new distance for vertex 5, which is 6 for vertex 4 and then plus 1, which is 7. But 7 is bigger than the existing 6, so no change. Moving on to vertex 5. We get a new distance for vertex 3, which is 6 plus 1, 7, and this is a shorter distance, so we update. This completes iteration 1, and this is the list of distances after iteration 1. Now let's move to iteration 2. Again, we start at vertex 0, and we see that we do not get any new distance for vertex 1 and 5, so nothing to change. Moving to vertex 1, again no new distance for vertex 2. Moving to vertex 2, we get distance 8 for vertex 3 and 6 for vertex 5, and none of them are better, so no change. Going to vertex 3, we get a new distance for vertex 4, which is 7 minus 2, 5, and this is a better distance, so let's update it. Now going to vertex 4, no better distance, so no change. Going to vertex 5, again nothing to change. Now it's easy to see that the next iterations will not change any values, which means that we have reached the shortest distance. So we actually did not need all the 5 iterations for this graph. We actually solved it with only 2 iterations. But in worst case, you will need all the iterations. Now here are 2 important facts about this algorithm. We can stop early if all the distances are unchanged after some iteration. Now to detect negative cycles, we will iterate once more and see if any distance changes or not. So after all the iterations are done, we are guaranteed to have the shortest paths. But if we see that some distance keeps changing even after that, we can be sure that there is a negative cycle. So to detect negative cycle, just iterate once more. Now that it is done, let's write the code. And as before, I will use C++. So first I will include all the necessary header files. Then I will use these namespaces, so let's just put them here. So instead of writing std every time like a barbarian, this is a better approach. Now this is our main function. So inside the main function we define our graph, and as before it will be the adjacency matrix form. So this is the adjacency matrix graph of the current example. And as you can see, this matrix is not symmetric because the graphs are directed. And then we call the function Bellman Ford and pass the graph to it, and also the index of the source node or the source vertex, which is 0 in this case. Now let's write the Bellman Ford function. So this will be a void function which will take a matrix as input and an integer as the starting node. So first let's get the number of vertices by calling the size function on the graph and create a distance vector of size v, which is the number of vertices. Then I call the fill function and fill the distance array with the maximum value of an integer, which acts as infinity in this case. So for that I use the numeric limits template with the int class and call the max function, which will give me the maximum value an integer can store. And then we set the first distance to 0. Now this is a loop. So as I said in the example, our loop will run v minus 1 times. V is the number of vertices. So at every iteration we will look at all the vertices. And for all the vertices we will look at all the outgoing edges. So here I am actually iterating over all the edges. We will just check if these are outgoing edges or not. So here we will write an if condition. So first thing we will check if graph ij is non-zero. So if graph ij is 0, it means that there is no edge between vertex I and vertex j. So in other words, this is not an outgoing edge from vertex I, so we do not actually care about that. So if it is an outgoing edge, we check that it is not infinity. And as before in case of Dijkstra's also we checked this, because in next step we are going to add something to it. So if we add something to the maximum value an integer can store, it will overflow and it might cause problems. So before adding something we are checking if it is infinity or not. So if it is not infinity, we can add the cost of the current edge. So here we are basically checking the edge between vertex I and vertex j. So if distance of I plus the time or the cost of the edge between I and j, so if it is less than distance j, we have got a new distance or for the jth vertex. So we update it. And that's about it. Now we can just print our distance. And this is the result that we will get, which agrees with the example we saw before. So this was Bellman 4. If you like this video, don't forget to hit the subscribe button. Also don't forget to hit the bell button